在 LT 跟 WiFi 的 offloading。好，那经过早上的这些keynote 一直到我们下午的第一个 session， 各位可以了解到说，在各个不同的技术不管是 cellular 或是 connectivity， 其实它都有共同存在的必要因为我们的目的是希望说可以提高更多的这个 throughput。但是同样的技术存在的时候，除了互相运用之外，那另外干扰也是一个很重要的一个课题。那所以接下来的这个 session 会有我的同事 Mr. Thomas Kneidel。Thomas is also one of our product manager from headquartered in Munich. He is mainly responsible for also CMW 500, but mainly for Wi-Fi and also for LTE offloading. So he will introduce what is our point of view of coexistent interference and also the test solution. So now it's your turn.
Thank you very much.
Okay.
Thank you very much, Bill. Welcome to this last session of the day about this Wi-Fi, not Wi-Fi coexistence interference, test possibilities. You introduced me already. My name is Thomas, coming from the headquarters in Munich, and I'm already for many years coming here 2 times a year to Taiwan, explaining especially aspects about Wi-Fi testing, which is my most favorite topic. The big difference to Germany and Taiwan, I found out, is the temperatures. Germany, usually the temperature outside of the house is much colder than inside. That's totally opposite to Taiwan. If you leave the house, you don't think about it's cold outside, you always have to think it's cold inside when you enter a house. So, in the meantime, it's not such cold than in the session of Günther, 1.5 hours before. And I will try to keep you warm in this topic. So, coexistence interference. So when I got my first phone, it was a pure GSM phone. That was quite simple, easy word at that time. And if I compare my GSM phone of 10, 15 years ago with the phone I have today, that's a totally difference. Nowadays I have so many radio access technologies on my device, and even in the rooms you have now the Wi-Fi everywhere, and you have the LTE, you have the Bluetooth, you have so many radio access technologies. And that really cause a headache of all the developers of such smartphones and tablet PCs. And I want to stress this point about the interference of this radio access technologies, which is the reason for that and what we can do against that. You have a handout of a presentation. In the last 2 weeks I did some slight changes. I added a few presentations. And if you have a need for that, to get that at PDF, please contact my colleagues of Rohde and Schwarz Taiwan. They have the PDF of this presentation which I held now. First of all, if we speak about interference, coexistence interference, we have to distinguish 2 different situations and scenarios. One is the external and the other one is the in-device. So, have a look on what's about external, and the external I again distinguished in between 2 cases, the far field and the proximity. What the far field and what I want to show with the far field is, for example, if you have a Wi-Fi connection between your smartphone and a Wi-Fi access point, there might be, that is the connection of your smartphone to Wi-Fi access point. There might be in the room or in the surrounding additional Wi-Fi access points. This additional Wi-Fi access points might cause interference to your Wi-Fi connection, which you have in between you and your access point here, due to the fact that the channel gap in the Wi-Fi is usually only 5 megahertz, channel by channel, but you occupy usually 20 megahertz. And if this access point, if you're using here, for example, channel number 6, and this is channel number 7, and this is channel number 8, then they would have a kind of overlapping and your performance would be reduced. Besides this access points here in the surrounding, which might reduce your capabilities of Wi-Fi reception and transmission, maybe other access points or other radio technologies like the LTE or WCDMA or whatever else might limit your capabilities. I will come to that a little bit later. The other interference is that proximity. it's a different situation. Here in this case, I have a smartphone with connection to an access point, and other access point in the surrounding might disturb me. The situation which I have here might be two users sitting close to each other. One has a Wi-Fi connection to an access point here in the room. The other one might have an LTE connection to an access point outside of the house, to a base station. And these two smartphones of maybe two users sitting close to each other, they have an interference from one device to the other device. Or the situation might become more critical as soon as these two users are sitting maybe in a car, in a very closed environment, and both are transmitting this max power, then the interference might be much higher. The next possibility of interference scenarios I want to stress are the in-device coexistence interference. And the in-device coexistence interference is what I mentioned before with the smartphone of today or tablet PC. And if you imagine how many radio access technologies you have nowadays on a smartphone or a tablet, you have not only, as I mentioned, the GSM 20 years ago, now you have the LTE, you have the GPS receivers, you have Wi-Fi, the Bluetooth, the Zigbee, and many of them are operating either on the same frequency or on adjacent frequency bands, which have an influence to the neighbor frequencies. So you see here the situation I mentioned already. You have here on one single device the interference. The external interference, which I mentioned at the beginning, was either from your DOT to an access point and you are interfered by other access points, or two people sitting with two different kind of smartphones, each next to each other. But now we have the situation that you have the interference on the same platform, on the same hardware. And you see here that you have maybe on such a platform the Bluetooth and the Wi-Fi going out on the same antenna, the GPS receiver, the LTE. And the situation will be that two radios, let's think about two radios, makes work a little bit easier, that two radios are operating simultaneously. That means you might have, let's say this is a Wi-Fi connection, and that is an LTE connection, and then during you have Wi-Fi and LTE, in this example, operating simultaneously, then the Wi-Fi transmitter is not only transmitting to the access point, it's also transmitting to the radiation to the receiving antenna of the LTE, and then you have here this Wi-Fi, in this case, as an aggressor, or an interferer of the, in this case, the LTE receiver. This is the victim. So in this case, we speak about an in-device coexistence interference. The advantage here, what we have compared to the other one, here we have the interference on one hardware platform. That means we might have possibilities for mitigation to reduce this interference by some techniques which I'll explain in the next slides. The other one, if we speak about the external scenario, when we have two platforms, the interference is limited only to radiation. In this case, we have not only radiation, we have also some conducting effects in between antenna, which cause us headaches. And the big disadvantage is here, the signal strength. The signal strength of this interferer, of this transmitter, is much, much higher than it would be maybe the base station of the LTE or the Wi-Fi access point to the receiver. This transmitter here has a maximum impact and signal strength on the receiving side of the other radio access technology, and this causes us some headaches, but there are some possibilities to reduce this interference. So what technologies I'm speaking about, what are these typical candidates which could interfere to each other? There's on one hand side, on the left side, you see all the cellular technologies, the LTE, the GSM, WCDMA, CDMA 2000, they are on the one hand side. On the other hand side, you have the Wi-Fi, the Bluetooth, Zigbee, Z-Wave, and not least the GPS receivers. The GPS receivers, which are transmitters, which are satellites, are transmitting in the frequency range of about 1.5 gigahertz. They are also in this scenario, and in this case, due to the fact that we are only receiving them, the GPS receiver on the smartphone is a victim in any case and would be interfered by other radios. So there are some techniques and possibilities, countermeasures, that you can limit and fight against this interference. So as soon as we speak about common, homogeneous wireless technologies, usually this modern technologies like GSM, WCDMA, LTE, they have different possibilities that even if you have two users, GSM users sitting each to the next other, using the same frequency band, but how they can manage that they don't interfere. The GSM, for example, is using the TDMA, the time division multiple access. That means every user has a special time slot, and his transmission or reception is only limited to this time slot. And the next time slot is reserved for another user. So by using this time division multiple access, there's a possibility that you can operate on the same frequency, same time, sitting each other very close, but you don't have an interference from one to the other one. The other possibility is the frequency division multiple access. For example, that for the downlink and the uplink, you're using different frequencies. That means that the downlink and uplink is not interfere the other one. And last but not least, the CDMA, the code division multiple access. In this case, we are transmitting on the same time, on the same frequency, multiple users, but each transmission is coded by an orthogonal code, and you have the possibility to separate this signal as soon as you know the code, the orthogonal coding of each of the subscriber, and then you have the possibility, even if they are operating same time, same frequency, you could distinguish the signals and there is no interference. There are other possibilities. In addition, you see the CSMA, the carrier sense multiple access, collision avoidance. That is, for example, a protocol which is in use as soon as you use the Wi-Fi. That means if two people are sitting in a room using the same access point on the same frequency, each of them is monitoring in the air, is detecting is there a signal in the air, and as soon as it detects there is no transmission, there is nothing I can hear, then you use this for transmission and to avoid some collision and interference of the other one. There's another technique is in use, it's quite similar, the LBT, the listen before talk. I'm quite sure you're aware that LTE, the LTE now, the ZigBee thinks about to use LTE as well in this ISM band together with Wi-Fi, and to avoid that the LTE, which is now sharing the same frequency band with Wi-Fi, does not interfere each other. This LTE is now doing such a kind of listen before talk, which is quite similar to this CSMA collision avoidance. That means this LTE is first listening if the channel is free and if there's nothing in the air and there's no signal, and then it's transmit to avoid interference, interruption of other ones. There are other technologies or possibilities to avoid such collision and interference, the so-called request to send and clear to send. That is another protocol which is in use in Wi-Fi world as well. That means only one who wants to transmit get a so-called token and is transmitting as long as he has the token, then he gives it back to the base station, and the base station as the access point gives this possibility, this token to another subscriber to avoid that two don't transmit at the same time on the same frequency. So when we speak about interference of two radio signals, we have also to think about a little bit some mathematics and some science. There is, of course, a loss of transmission power from the transmitter to the receiver, this path loss. The question is how much loss of energy we are losing in between the transmitter and the receiver. And this formula which you see here, it has on one hand side the wavelengths of the signal, and on the other hand side you see here the D, that is the distance in between the transmitter and the receiver. You can write the same, not with the wavelength, with the frequency, and then based on this formula you would be able to calculate the attenuation, the loss of signal strength in between the transmitter and the receiver. And that we have to take in account as soon as we start to analyze the interference in between two radio technologies. If we take the example of 2.4 gigahertz, that means the frequency range we use here about 2.4 gigahertz in this formula, we would get this value. That means we have a value of about 40 dB attenuation, and then in addition, depending on the distance in meter, we have then the value about what attenuation we could expect in between the transmitter and the receiver. And due to the fact that this values here, this formula is based on a free space propagation, ideal conditions, but usually inside of a room we have shadowing, we have reflections. There is another formula more precise. So we have for the indoor model, we have this value, you see then a little bit modified for a distance above 8 meters, this formula, and this gives us these typical values that we usually could expect an attenuation between the transmitter and the receiver, usually about a value between 60 dB in a distance of about 10 meters, and about 93, 94, 95 dB at a distance of 100 meters. That means we have to reduce this attenuation from the transmit power of the sender, of the transmitter. So have this in mind, we have typically values about 60 to nearly 100 dB of attenuation. And on the next slide, you see typically transmit values, transmit power values. So a base station, a cellular base station, LTE, WCDMA, maybe have a transmit power of 43 dBm. So and when you think about that, you have maybe an attenuation about 95, 93 dBm. That means you have at the receiver side, on the receiver side of your smartphone, you might have a signal strength of about minus 50 dBm. Or in case of wireless LAN, where the access point is transmitting with 20 dBm, but the distance is not such high. We don't have 100 meter, maybe we have only 10 meter with 60 dBm. That means the signal strength in the same case here is again about minus 40, minus 50 dBm on the receiver side of my smartphone, of a Wi-Fi signal or an LTE signal. So now take that in account, that if you have your smartphone, the signal strength of the access point or from the LTE base station is round about, let's say, minus 50 dBm. That is the signal strength which I'm receiving from the base station or from the access point. But on the other hand side, I have at the same moment on this device a transmitter, a Wi-Fi transmitter, which is transmitting with 20 dBm. That means I have on one hand side receiving an LTE signal with minus 50 dBm and have at the same time a signal of plus 20 dBm of the Wi-Fi transmitter on my same device. That means this Wi-Fi signal is such strong much bigger than the LTE signal which I receive from the base station. And now if these frequencies are very close, then I have a big impact on my LTE receiver in this case, and I might have problems to detect the LTE signal. So there are several reasons and sources which are causing my interference. This is on one hand side the transmitter noise. That means usually a transmitter is not transmitting a clear signal. It transmits, in addition to the carrier, some noise which we try to filter and block down. And this spurious emissions, this out-of-band transmission, this have an impact on my receiver and reduce my sensitivity. Then I have a receiver blocking, receiver intermodulation, and harmonics distortion. I come to that now in detail. First, with the transmitter noise. The reason for the transmitter noise is usually a phase noise on my local oscillator. This would be the ideal, the perfect local oscillator. But usually our local oscillators, which we have in use, they have a certain phase noise. And now if I generate a signal, for example this red one, with my real local oscillator, then this might be my transmitted signal. You see, it's not anymore such nice arrow. I have now left and right some out-of-band emissions, which increase my noise of the receiver of my wanted signal. That means the phase noise of this local oscillator is causing an out-of-band transmission of my adjacent channel. For example, this is the LTE transmitter on my same device. So this LTE transmitter is not only generating a signal on the LTE frequency, due to the phase noise of my local oscillator, it's generating some frequency parts, some emissions, spurious emissions, which are now in the receiving band of my wanted signal. Of course, such increase my noise level on the receiver side and reduce my receiver sensitivity. The other point are the receiver blocking. The receiver blocking is caused by the limitation of the dynamic range of my amplifiers and my analog digital converters. As soon as I have a very strong signal next to the wanted signal I have, so that means the sum up of my input signals, the total sum of my input signals, the signal strength, is above a certain limitation. The amplifiers have a problem, and you see here, if this wanted signal, for example here, the same signal I am receiving with a strong neighbor channel signal or without, the sensitivity is different. So the dynamic range of my amplifiers are strongly impacted or influenced by some strong neighbor signals. That means I see this same signal with a higher sensitivity if that is switched off, compare if this is present. So this strong neighbor signals, again, reduce my receiver sensitivity, and with the impact that my receiver sensitivity goes down and I have more problems to detect such a signal. The third influence or source for interference are these receiver intermodulations. They are caused by non-linearities of the amplifier and components on the receiver part. So as soon as I have two or more signals on my receiving part, my receiver again, based on the non-linearity of my components, are creating additional signals. And the worst one, or which has the biggest impact, is the third order intermodulation interference. The third order intermodulation is causing me additional signals, creating signals which are usually not in the air. So if I have maybe this signal number 1 and signal number 2, which have a certain distance, then the third order modulation of these two signals are creating left and on the right side such intermodulation products. And the distance, this distance here, depends on the distance of frequency 1 and frequency 2. And if these two signals are very close, then they are the third order intermodulation product maybe fall in the bandwidth of my receiver. That means if this second signal which I'm receiving, and maybe it's not my wanted signal, it's maybe the neighbor channel signal, if this neighbor signal is causing this intermodulation product, third order, which is now in the bandwidth of my receiving signal band, and again, this causes some interference and there are these unwanted impacts. The last one, number 4, are harmonics. So as soon as I'm doing signal generation, I'm not only creating or transmitting, maybe that is a signal I want to transmit, again, based on non-linearities, I'm creating integer multiples of this frequency, which then are totally far away in other frequency ranges, and they might cause some interference. I will show you on the next slide that, for example, in case of an LTE signal here, which I'm transmitting here, multiple of this frequency, the double of this frequency, maybe fell into the frequency range of my GPS receiver. And the third order might fall into the frequency range of Wi-Fi. So that means I'm transmitting here an LTE signal, and this signal far away in the frequency range of the GPS receiver, the harmonic of this LTE signal are causing here some interference, and the third harmonic might cause some interference in the 5 GHz band of my Wi-Fi signal. These are very sensitive frequency bands, which we have usually to analyze more in detail. You see here in the middle the ISM band, where we have the Wi-Fi, the Bluetooth, the Zigbee in operation. So usually they are sharing here this 2.4 GHz frequency band, and left on the right side you see different LTE bands which are in use. Very close, only with a very small gap here, we have the LTE band 40, which is operating in a TDD mode, that means on the uplink and in the downlink. And on the right side we have the band 7, which is an FDD mode and only operating in the uplink mode. So that results in different influences. Of course, the wireless LAN could influence both sides, and here this one only in the uplink would have a possibility to have impact on the Wi-Fi signal. The ISS band, which I mentioned already, which is in use by the Wi-Fi, Bluetooth and Zigbee, you see that they are sharing here this frequency band of 2.4 GHz. You see here several channels are specified, and of course if you have the Bluetooth or the wireless LAN or the Zigbee operating at the same time, they would interfere each other due to the fact that they are operating in the identical frequency band, but due to some tricks and some technique we can limit the interference of each other. I will come to that a little bit later, or maybe I can mention already now. One of the techniques which is in use here, for example, in case of Bluetooth, is this adaptive frequency hopping. That you are not permanently maybe use one of this Bluetooth channel, that you change every few milliseconds the channel and jump to another channel that makes you resistant against narrowband interference. So everybody in Oxen have several techniques to avoid the interference of each other. In the case of, I mentioned already, harmonic distortion, that means the integer multiple of, for example, LTE signal of band 13 and band 14, the second harmonics are here in the frequency range of my GPS receiver. That means if I'm permanently transmitting on LTE, my GPS receiver might get a problem to receive and detect the GPS signals. Same situation in case of wireless LAN in the 5 GHz band. Here we have the third order harmonics, and here we have, depending on which channels, different kind of LTE bands where the third order harmonics of such a signal would limit my receiver quality. There are a lot of combinations which technology might have an influence on the Wi-Fi receiving. And there's a paper of this GWG where we have listed all the combinations of Wi-Fi channels and what kind of cellular technologies based on which frequency, which kind of harmonics would have an impact on the Wi-Fi channels. So this association was already analyzing all the scenario, and if you have a need to analyze that by yourself, this is a very good documentation where you find all the lists about the impact of harmonics, in this case on the wireless LAN reception. Very critically, I mentioned already, even if they're not operating in the same frequency range, but there are some impacts from the LTE to the Wi-Fi and as well from the wireless LAN up to the LTE receiver, which I want to go more in detail in the following slides. You see here the example, not an explanation. How is the situation? Here in this case, I now have the situation that I want to receive an LTE signal on the band 40, and a wireless LAN channel, in this case channel number 1, which is maybe very close to this band 40, is influencing the LTE receiver. How is the situation? We have now here in-device on one common platform on the smartphone, the Wi-Fi and the LTE radio access technology operating at the same time. You see here on the right side the wireless LAN transmitter on my smartphone. In this case, maybe channel number 1. Channel number 1 of my Wi-Fi transmitting with 20 MHz, a 20 MHz signal. The transmission, the data transmission, the signal strength of my Wi-Fi signal here is about 20 dBm. And of course, here I'm here in the Wi-Fi channel number 1. I have to follow, I have some filters which now are limiting my spurious emission. Then I have in addition on my smartphone, of course, some isolation in between the antennas. This typical, such an antenna isolation is of between 10 to 30 dB. So that is something which we have to take into account. Due to some constructions, you might have a channel and antenna isolation in between the Wi-Fi transmitting antenna and the LTE receiving antenna. You could estimate an isolation about 10 to 30, typically 10 to 30 dB. So, but not least, when I have now the Wi-Fi transmitter transmitting here on channel number 1 with 20 dB, and even I have some bandpass filter, I have this antenna isolation This is resulting here in LTE interference signal, which is much and far too high and much bigger than the expected LTE signal which I'm receiving from my LTE base station. You remember? Typically, we would expect an LTE receiving signal here with a value of about -50 dBm. This here is about +20 dBm. So maybe we have some filtering and we have a channel an antenna isolation of 30 dB. This LTE interference which we have here will result that you will not receive this LTE signal anymore. So we have to look some for additional possibilities what we can do to avoid such a scenario that this Wi-Fi transmitter on channel number 1 make a reception of an LTE signal at the same time impossible. So you see here a screenshot out of a spectrum analyzer where we did this recording of such a signal. This was a real Wi-Fi signal, here the brown one. You see here channel number 1, and you see as a separate measurement without the Wi-Fi, you see here the LTE band 40. And you see here that here both channels, that both signals are already inside in the reception of the other one. On the other hand side, on the other side of my panel, of my ISM band, channel number 13, you see here channel number 13, Wi-Fi channel number 13, and the LTE band 7 on the uplink, that they are also very close to each other and would cause some interference. These are typical devices where we have such scenarios where this coexistence of two different radios at the same time may cause some headache. You have here this LTE WLAN portable routers where you're from one hand side, you have an LTE connection, and on the same time you want to transmit all the signals which you get from the LTE connection, you want to spread by Wi-Fi inside in the room. Or you have here the GPS receiver and the LTE. I mentioned already here in this case the band 13 and 14, the second harmonic of this LTE signal might destroy the reception or makes the reception of such a GPS signal impossible. Or here in this case LTE and WLAN offload. That is also a possibility that Wi-Fi and offload and LTE operating at the same time. That is a possibility that you can shift a data transmission from an LTE connection to the Wi-Fi connection, but you still have the LTE connection in operation. And in this case, again, you have such an LTE WLAN interference or such a scenario with the Bluetooth headset on the LTE connection. Again here, such interferences. How you can test such a scenario, and now coming to that, Rohde and Schwarz is a test equipment producer. We have the possibility that we can simulate such scenarios by our test equipment and give you the opportunity to analyze such scenarios. Our test equipment, our radio communication tester, CMW 500, has the possibility that he can operate two radio access technologies at the same time. So we can run, for example, an LTE connection and a Wi-Fi connection at the same time. We have the possibility to define exactly any kind of transmit power. We can control the device under test. We can define exactly power measurements and frequency settings. And based on that, we are maybe here in this case, you can set up a connection, a Wi-Fi connection to your device under test and an LTE connection. And then you have the opportunity to analyze the influence, for example, of the Wi-Fi transmitter on the LTE receiver and vice versa, if the LTE transmitter to the Wi-Fi receiver, and to make sure that you only limit your measurements to this interferer caused on your device under test. You can all do this measurement in such isolated chambers which are radiated, isolated, that you only measure the influence, the in-device own cost and impacts for such measurements. So we provide here the perfect solution for analyzing such in-device coexistence interference tests, and we are not the only one who thought about these ideas. As well, the Wi-Fi Alliance wrote some papers and specifications, and they specified what you can do to analyze this in-device coexistence interference in test setups. There are existing some papers and specifications how the test setup have to be done, and they are using our Wi-Fi and LTE tester for such test setups. So how you can measure and analyze or evaluate the desensitization, the impact on the receiver side. Of course, you have on one hand side the transmitter, the interferer, which influence the receiver, and you have to evaluate this impact, this negative impact of the transmitter of one radio access technology on the receiver of the other radio access technologies. There would be, in principle, the possibility that you base this measurement on a throughput measurement, that you might want to check if I have the one interferer, let's say the LTE interferer, and I do the Wi-Fi connection and I check the data throughput. Which impact does this LTE transmitter have on the throughput? But a throughput measurement, that means bits per second which are transmitted, is not only limited by the quality of the receiver, it's also limited due to some power processing and window sizes and error corrections which you are running next to a receiver inside on your device under test. And it makes it complicated to compare two different devices each other. It's much better to do such a measurement based on such an evaluation, based on the receiver sensitivity, based on a packet error or bit error or block error ratio measurement, and check and take the bit error, packet error ratio measurement as a reference to evaluate such an impact. And so what we have done, or what we did, is that we are using this receiver sensitivity as for evaluating the interference. And how is it used, or how is it implemented? The IEEE specifies the receiver sensitivity on certain power levels for different kind of modulations when you have a packet error ratio of 10%. That means usually you reduce your output power or your transmitting power, you reduce the transmit power of your measurement equipment, you reduce the output power, and at the same time you do a packet error ratio measurement of your Wi-Fi receiver, and as soon as the packet error ratio hit the 10% limit line of your packet error ratio measurement, this is a receiver sensitivity which you then are taking into account. And what we are doing now is, for our analyzing of this in-device coexistence interference, that we do first a receiver measurement without the interferer, and then we repeat the measurement with an active interferer. And this distance, this one is a blue curve without, the red one with the interferer, and this distance, this desensitization, that is the value which we take in account for the measurements to compare to different implementations of devices. So this is a desensitization referred on the 10% packet error ratio for evaluating the in-device coexistence interference. So there are some possibilities to limit the interference. There is, of course, the transmit spectrum mask. transmit spectrum mask is something which is specified by 3GPP or IEEE, which each of your transmitters have to follow. And that means outside of the band, you have to reduce the transmitted spurious emissions must be under a certain limit. The next possibilities are the antenna isolation, the localization, orientation, shielding. That means that you look for smart locations and places of your Wi-Fi and LTE transmitting and receiving antennas, and you locate them in such a way on your smartphone or tablet PC that maybe have a maximum distance to each other, and where you have the possibility maybe to build a shielding around to avoid the interference of each other. Of course, filtering on the transmitting and receiving side by bandpass, low-pass filters, and the beamforming and interference cancellation. These are possibilities based, but this is only limited for external signals arriving, not for in-device coexistence. Disadvantage of this static and possibilities which are mainly limited to the physical layer. The big advantage here is they are permanent. They are always active. That means even if you run your smartphone in a single radio mode, they are still active. And all these measures have a negative impact of your performance. That means even if you run this, your smartphone in a single radio mode, that you only use the LTE or you only use Wi-Fi, they are permanent active and reduce the performance of your device. There are much better possibilities, we'll show you on the next slide, and more flexible, which you only activate when there is a need. The other possibilities, of course, these measures which are based on the physical layers may make your smartphones bulky, big, heavy, expensive. That is something which the manufacturer try to avoid. On the higher layers, on the MAC layer, if you read, this was before the slide, it was, these measures were limited more or less to the physical layer. Here we have now the possibility on the MAC layer to use more intelligent measures to reduce the interference. And these are again here limited to the MAC layer, and they are dynamic. You can activate them only if there is a need, and that means they don't have a negative impact on your performance. These are on one hand side the frequency scheduling. That means as far as the transmitter and receiver far away, as less impact you have, negative impact the transmitter have on the receiving side. The transmit power, if you have the possibility, again here, frequency shifting or this dynamic frequency scheduling is of course limited. You have only limited possibilities to move the frequency far away from the receiving side, or vice versa, the receiver far away from the transmitter. There is limited possibilities. The same with the transmit power control. There would be the possibility that, for example, the base station or the network operator gives the command to reduce the output power of your signal, or for example, if you're closer to an access point, that you reduce by yourself the output power. There's possibilities that you maybe reduce the channel bandwidth or the resource blocks in case of LTE, which makes the bandwidth smaller and the gap in between transmitter and receiver increase. Then we have the possibility of time sharing. That means we try to avoid that both are operating at the same time. There are possibilities as soon as the transmitter is aware that there is a receiver which I can interfere, there's a possibility that we might find a way that we avoid a collision by time. That means that we may go in a sleep mode when the other one is in the transmit mode. And the other one is the adaptive frequency hopping, which I mentioned already in conjunction with Bluetooth. That means as soon as we detect that there are other frequencies which are occupied by other transmitters, So we avoid these frequencies and we don't use this frequency anymore. So if we go about frequency scheduling, you have this picture in mind before. The idea behind this, that either the receiver, in case now we have the situation, it's a Wi-Fi receiver, that we might change the frequency of the channels. You remember here that's the LTE band 7 on the uplink, and we have here on the same side the Wi-Fi channel number 13. As soon as we would move the Wi-Fi channel from 13 to 12, 11, 10, we would here increase the distance in between the LTE transmitter and the Wi-Fi receiver. That would be already a good idea. Or if we find a possibility that we move the LTE transmitter more to the right and to increase the frequency gap in between both transmitter and receiver. You see here analyses which we have done with our CMW 500. We have an automated program where we can run such tests in an automated form. What you see here is, we have here this light blue line is a wireless LAN receiver without anti-interference. So we let run this Wi-Fi receiver is operating without any LTE signal in the air. And now what we have done the LTE active, and we were using the Wi-Fi channel number 13. Wi-Fi channel number 13 is now the most closest Wi-Fi channel to the LTE band 7. And you see here that now the receiver sensitivity of my Wi-Fi receiver, when the LTE transmitter is active, is very poor. But as soon as I move my Wi-Fi receiver to channel number 12, I have already an improvement. That means the signals I can receive could be lower than this one. That means you see here on that curve, as more as I move my Wi-Fi channel far away from the LTE transmitter, the quality of my Wi-Fi receiver is increasing. So you see here in this case, we are here using the Wi-Fi channel number 9, and the Wi-Fi channel number 9 already is much far away from the LTE transmitter, and the Wi-Fi receiver here is reasonably good, and the interference is quite limited. The other possibility is to reduce the power. Again, example, we have the Wi-Fi receiver, which we stay now constant on this channel, but we try to reduce the output power of our LTE transmitter on our smartphone, for example. So what happened, as soon as we reduce the output power, the interference of our Wi-Fi receiver will be reduced, and the Wi-Fi receiver, maybe we could improve the performance. Let's see what happened here. We have again here the situation that we have here the Wi-Fi receiver without any interference. And as soon as we are commanding this, the LTE transmitter to transmit with, for example, 23 dBm, that is this curve, the Wi-Fi receiver is very poor and very much interfered by the LTE signal. And you see here we have the possibility with the CMW that we can command the device under test to reduce the transmit power of LTE. And that means as more as we are reducing the transmit power of LTE, the quality of our Wi-Fi receiver, the receiver sensitivity of our wireless LAN receiver is improving. So you see the impact of the reduction of the output power of the LTE transmitter have a direct impact on the quality of our Wi-Fi reception. You see here's an example that this is here the uplink power, LTE uplink power, and this is a desensitization. That means how we make the receiver quality worse of the Wi-Fi transmitter. And as soon as we are reducing the output power of the LTE transmitter, you see the negative impact on the Wi-Fi receiver is reduced to a minimum, is lower than the output power is of the LTE transmitter. The other possibility is that we could maybe limit the resolution bandwidth, the bandwidth of our LTE transmitter, which again has an impact on the quality of our Wi-Fi receiver. You see here, again, the blue line is the Wi-Fi receiver without interference, and you see the Wi-Fi reception here with an LTE, simultaneous LTE interferer, and you see as soon as the LTE bandwidth is only 5 megahertz, the negative impact on my Wi-Fi receiver is going down to a minimum. The other possibility is the possibility of the allocation of the resource blocks, that depending how I place the resource blocks on LTE, so if the base station, the LTE base station is aware that I have on my smartphone a Wi-Fi reception simultaneously running, the Wi-Fi base station would be able to command the device under test, the smartphone, that it should use special resource blocks which help you to increase the frequency gap in between the Wi-Fi receiver and the LTE transmitter. You see here that we have here the Wi-Fi channel, the Wi-Fi channel 13, and depending how I place my LTE resource blocks, I can move the spectrum of my LTE